So to prove the theorem, what we would like to do first is to translate some of the definitions from the PAC model into our current setting for Boolean functions. And the first translation we will make, or adjustment we will make, is to take the concept of the error function which we had used till now, where h is the hypothesis, and in order to find out how far away we are from the concept we are trying to learn, what we had done was to take the difference between h and g, the function we want to really learn, let's say, and take the difference, square it, and take the average value. So we will now define a concept which is a bit more specific to what we need, which is called the distance. And that's again between the hypothesis h and the function f that we are trying to learn, which is, and if you remember this notation, it simply means that's the probability of drawing inputs to this function f, or for that matter to h, n at a time. These are n tuples uniformly at random. So then you just calculate the probability where of hx not equal to fx. So if it's equal, that's good for you. If it's not, then that is the distance. You're further and further away the bigger this average. So you want small averages is the idea. Okay? So the probability is small, then the average would be small too. Now these two forms, the thing that we've been using before, which is the error, and this concept of distance, it turns out are related. In particular, I'll quickly walk through and show you in the next few minutes that the concept of distance is always better. It gives you a better estimate and therefore a more conservative bound than expectation. So we can always assume that if you're doing better at distance, you're doing better with the old form. You're always doing better than the old form which we've been using with the expectation. So to understand that, we will introduce a small concept. It's a very simple concept, and this is standard to mathematical reasoning in many ways. There are these functions which are called indicator functions. These indicator functions are useful to know about in general, and we'll use them in a very almost trivial way, written I, which take on a value 1 when something you want happens, will take on a value 0 if something that you don't want happens. So what we are going to do is to define this indicator function to flag for us whenever fx is not equal to hx. So it will raise its arm and say, I'm 1, they're not equal. So now summing the probability of being able to say that something is not equal through this indicator function, right? So distance fh, we defined it to be the probability of hx not equal to fx, which if you average, since it's a uniform distribution, if you average over all possible inputs, it is just the sum of the indicator variables and the expected value of that sum. It's a very straightforward thing to conclude. Now, okay, so we have that. We'll keep that in our pocket and then say, okay, fx minus hx, the whole squared, is always greater than or equal to 1 because it takes on a value of, basically, it can either be 1 or bigger, and it's a square, so it's positive. So knowing that it's always bigger than or equal to 1, right, and of course it's 0 otherwise, under the conditions that I have stated on the slide there. So distance fh is the expectation we just described here of the indicator function, but this indicator function is less than or equal to the same expectation over fx minus hx square, because this term under the expectation is bigger than or equal to 1 when this term is 1 and they're 0 at the same time. So since one term is bigger than or equal to the other term whenever the first term is 1 and they're equal when it's 0, then this inequality holds. So our notion of distance is giving us a tighter estimate than the estimate that we used to have through the concept of error. So we can now replace it because it's more conservative in that sense. So what's the theorem we were trying to prove? The theorem we were trying to prove, and I've said this before, so I'll walk through this quickly, is learning algorithm A has, through an oracle, access to randomly chosen examples as inputs. Then A can, through this oracle, also find this high value subsets F, on which F's Fourier spectrum is epsilon by 2 concentrated. If you remember, I said we'll use epsilon by 2 for technical reasons. Then using time that's polynomial in the size of F, n, and 1 over epsilon, that's the extra time beyond consulting the oracle and getting the examples, algorithm A can with high probability output H, that is epsilon close to F. And our concept of error or quality will be based on this distance function. Okay? So that's the theorem we are trying to prove. So we'll proceed at a high level in 3 steps. In step 1, we'll develop an algorithm for approximating the Fourier coefficients f hat on the given set S. So if you remember, we are approximating at 2 levels. First, by looking at only some of the Fourier coefficients in order to be able to estimate the function f. But each Fourier coefficient was in particular being estimated because it's expensive to compute it precisely, and we use the symbol f tilde to represent its approximation. So now I'm talking about an algorithm for computing f tilde. And then what we would do is a method to build a provably good approximation for the true function fx building on step 1, and build on these 2 steps to say that the running time of the algorithm is in fact within the bounds that we want, and therefore we prove the theorem. So this algorithm now will be proved, as I said, will stage through step 1, step 2, and step 3.